This is lesson 2.5, part 1. So part 2 is going to be in a different video. This is going to be on the applications of dot and cross product. In this video, I'm actually going to be concentrating on projections. And so I'm going to warn you, projections can be kind of difficult for people. I'm also going to be going into algebraic proofs. And so if there's at any point you feel that, you have some questions or you need clarification, definitely message me below and I'll try to clarify. Okay, so projections. A projection is a perpendicular line from a point to another line or a plane. Okay, so for example, if we're talking about 3 dimensions, human shadows would be a really good example to talk about. So imagine that you have the sun shining on your head. Your head can be the point. Okay, what's going to happen is you're going to project a shadow onto a plane, which is the ground. In 2 dimensions, we can always think of a line projecting onto another line. I guess you can think of a sun still, and the line having a shadow onto the other line. Okay, so we can keep like that same scenario if you want to. But why talk about lines when we can talk about vectors, right? We're in vectors, aren't we? Okay, so you're like, she's just talking gibberish at this point. Let me show you. So here are 2 examples of a u vector and a v vector with a theta encompassed in between them, tail to tail. Okay, the left diagram has theta as an acute angle, and the right diagram has theta as an obtuse angle. All right, so what I have is a u vector, which I can also call OA, and a v vector, which I can also call OB. So let's project u onto v. I'm going to pretend that there is some sort of a sun that is then shining onto vector u, which will then project a shadow onto vector v. And it does so at a 90 degrees, so perpendicular. I'm just going to call this n. And v is bothering me, so you're going to go over here. Okay, so now I've projected u onto v, and I've created a shadow, but the shadow would probably be only along this line. I'm going to call that vector ON. So the projection is actually a vector. And for the rest of the video, I'm going to call it projection of U onto V. I know, right? You can write onto if you want to, but I'm lazy and so I put the arrow. Okay, so the arrow means onto. Now I can also figure out how long that shadow is, or that projection. And so I can find the magnitude of the projection vector. Okay, so that's what it looks like if your theta was acute. On the other side, we're going to talk about theta as an obtuse angle. You're still going to have your sun because I want to project u onto v, but what I'll have to do is I'll have to extend v this way and project u at a 90 degrees that way. Okay, so this is my n. And you'll probably notice that ON is now in the opposite direction. So the vector can be a negative vector. Just make sure that when we're talking about the magnitude stays as a positive quantity because it's a length, right? Like there's no such thing as a negative length. So this would still be called ON because it's going from O to N. And that's why I'm still going to call it the projection of U onto V. Everything that we had just talked about is in that cloud underneath, and the purple is just saying that the projection is a vector, but you can find the magnitude of it. In fact, let's do that. Okay, so this is going to talk about the magnitude. U is going to project onto V perpendicularly. Is that a word? I don't know. Okay, so you have your projection vector, ON, but I can definitely figure out the magnitude. Okay, but how do I actually find that? Well, I mean, you have vector u, you can figure out the magnitude of u, and so that's a right angled triangle. If I use cos, I have the adjacent magnitude of ON over the hypotenuse magnitude of u, and then I'll get cos theta. I can even rearrange that to get just ON by itself, which will give me the magnitude of this projection vector. Okay, now in purple, I have like a little side note. Just be very careful. I do want you to understand that cos theta has portions of it where it's negative. If we draw out, say, like the graph, this is all where cos is negative. Even if you think about like the cast rule, there's like quadrants where cos is negative. Okay, so I'm going to talk about like this quadrant specifically right here. Okay, and so anywhere between that quadrant, if theta is within 90 degrees to 180, unfortunately, this is going to be a negative number, okay, minus the negative number. And that could create a negative magnitude for ON. That means that we have to compensate for that by making sure that we do absolute value symbols for everything. Okay, magnitude is a length, which means that it should be a positive. All right, so we talked about projections, and I kind of want to organize us. So projections. Oh, I don't know why those dots appeared. Okay, let's get rid of that. This is what I'm going to be talking about in this video, because there's just, where did that come from? Why are you doing this to me? It's so sensitive. Holy cow. In this video, we're going to be going through a lot of things, and so the more organized I can keep you, the better you're probably going to understand. So I'm going to talk about what happens if a question asks you for a vector, like a projection vector, or if they ask you to find the magnitude. Okay, there are certain formulas that you can use for each one, and in fact, each one has two formulas, and you're going to be like, why does it have so many formulas? Well, you don't have to memorize all the formulas, but it's kind of useful because depending on what the question itself gave you, you can pick one of these four formulas and use it. And so if the question is saying, okay, find the projection vector, and I'm going to give you a theta. Well, if they give you theta in the question, then use the formula that has a theta. If the question doesn't have theta, then use a formula that doesn't have theta. Okay, so there's two formulas, one with a theta and one without. Same with magnitude. There is a formula with a theta and there's one without. And so if they ask you for the magnitude and within the question they give you no theta, use equation number 4. So here we get into the equations now. Okay, so in the box you should see a red formula, and that is equation number 1. It's used when we're trying to find the vector of the projection. Okay, so notice that I put a very big 1 on the left-hand side. So the projection vector looked like this. Remember, we had like an O and an N. That's made up of a magnitude and a direction. The magnitude we had already talked about already previously. And so let's just talk about the green for a second. The direction is created by the unit vector, and this should not be new to you, this formula. It creates your unit vector for V. Okay, and I've simplified it a little bit right over here. So what does that mean? Well, ON is created by a bunch of these unit vectors, and each unit vector has a magnitude of 1. Okay, so each one of these is vector V, right? Then you're going to talk about the magnitude. Well, the magnitude is how many of these guys do we have? 1, 2, 3, 4, 5, 6, 7. So the red vector is created by 7 unit vectors. The 7 being the magnitude, and the unit vector tells us the direction. And so in the box, you'll see that the formula has to be composed of both the magnitude and the direction. This is what we're going to use if we actually have theta, because notice that theta is given inside the formula. So if the question on a test says theta is 90 degrees, then throw 90 degrees into the theta. Okay? The black part is basically telling you, and why don't I stop scrolling so that you can read it. Sometimes you'll have a negative cos, like we had discussed before, if your angle is obtuse. Okay, so we had already talked about that. I'm just going to move on. What if you don't have theta? Okay, so if you don't have theta, this red formula is kind of useless. If you have like an unknown there, and you're trying to find the projection, which is also an unknown, that's too many unknowns. And so what we're going to do is we're going to try to create a formula that actually doesn't have a theta in it. Okay, so what I'll do is I will multiply this by the magnitude of v. So this is proof, guys. Okay, notice that magnitude of v over magnitude of v is 1. In that way, like, I didn't mess up the red formula at all. I didn't anger any math gods, okay? So I didn't change anything because I'm just multiplying it by 1. But if I take the top v, put it right here, and take the bottom v and combine it with this guy, what you'll start to notice is you have the dot product right there. And that eliminates our theta. Okay, so now I have a formula that has no theta in it. Okay, so this gives rise to our second formula in order to find the projection vector without actually using a theta. Now going into our two magnitude formulas. Okay, so what happens if we were given theta and we want to find the magnitude? We're going to use equation number 1. This is equation number 1, right? Because it has the theta. But now we're going to find the magnitude. Okay, so put your magnitude symbols along it. And basically anywhere where you had brackets, put magnitude symbols instead. Okay, so we're finding the magnitude of the v over v. We're finding the magnitude of the u cos theta. And I know I didn't write it. I didn't want to put a dot because I was afraid that you might think it's a dot product. And so just know that these guys are multiplying each other. Okay, so if I'm already taking the magnitude of v, the vector v over v, why don't I just say this is a magnitude of v and this was already a magnitude of v? Get rid of them. Okay, that just equals to 1, right? And so the magnitude of the projection is u cos theta, which we already figured out from the very first, this was our first slide all the way down here. See, we already figured it out. U cos theta. All right, that's our third formula, and that's if we have a theta. What happens if we don't have a theta? We're going to get into our fourth formula. Okay, so obviously use formula number 2. Equation number 2 was the projection vector with no theta, and we're just going to work on top of that. Find the magnitude. And anywhere you have brackets, put magnitude symbols instead. Okay, so what I can do is I can kind of cross things off. There's one up here and there were 2 down here. So that leaves 1 on the bottom. And this gives rise to our last formula, which is a projection of u onto v if we don't have theta. Okay, so it really depends on what your question is actually giving you. And you just have to kind of choose your formula accordingly. All right. If you need a break, pause it here. If you're ready to go, let's keep continuing on and we'll do some examples. Okay, so example number 1. If P, which is a coordinate, Q, which is also a coordinate, and R, also lastly a coordinate, they are all non-collinear points. Okay, so non-collinear means that they're not all along the same line. There may be maybe here's P, this one's Q, and maybe R somewhere over here. Okay, so all of those are coordinates. Find the projection of PQ onto PR. Okay, so PQ, like that. There's PR, and I want the projection of this one onto PR. Okay, so I'm essentially looking for that vector. Oh, and it's also asking you for the magnitude too. Okay, so why don't we do this in steps? The first step is, I don't even know what the vectors are. They didn't give me any vectors. The P, Q, and R are not vectors, they're points. And so the first thing I got to do is I actually have to find the vector PQ and the vector PR before I start projecting things. Okay, so let's give you some colors. I'm going to say this one is Q minus your P is going to give you PQ. Remember, it's Q minus P, right? Because it goes from P to Q. All right, so I'm not going to go over the math. You can take a look at it. The next one I'm going to do is I want PR, so I'm going to take R minus P, and now I have a very pink or magenta PR. Okay, so now that I have both my PQ and my PR, I can do the projection. And notice that in the example, they didn't give us a theta. So number 2, when I want to find my vector, I'm going to use a formula that doesn't have a theta in it. Okay, so if you remember, this is actually out of the 4 formulas, this is formula number 2. Okay, so I'm going to go PQ dot PR over the magnitude of PR squared, and that's going to be a times the actual vector PR, which will create a vector. Like this entire thing right here is going to give me a scalar that I'm now going to multiply with a vector. So my answer should look like a vector. Okay, doing the dot product, I get something like this. Okay, doing the magnitude, I'm going to do that Pythagorean theorem thing. Okay, and I'm going to get this as my answer right there. Now if I square it and square root, those guys are going to cancel out. And I will get, I'm going to just go all the way up. There we go. Negative 4 over 48, which I can then reduce and then also multiply in. Okay, so if I do that, I get 1 over 3, 1 over 3, and negative 1 over 3. This is the vector for my projection of PQ onto PR. If you want it to look a little bit nicer, you can always factor out the 1 over 3. Okay, now to find the magnitude, all I'm going to do is I'm going to take my projection vector and I'm going to do that Pythagorean theorem thing. But don't do it with these guys. Don't forget that this 1/3 is actually part of the vector as well. So I would actually use this vector to find my magnitude. So notice on the left-hand side, I did the square of each of those components, the sum of them, and then square rooted. So that Pythagorean theorem thing. And I get an answer of 1 over root 3 units. That's how long the projection is. Okay, now if I wanted to, I could always use, remember how we had 4 formulas? The very last formula, formula number 4, was a magnitude formula that had no theta. And so we could also use that and notice that we get the exact same answer. Okay, so moving on. Okay, we're making good time. An example of the cross product we had talked about before as the area of the parallelogram. Okay, so you know that the area of a parallelogram is base times height. Let's explain where the base and the height comes from. Okay, so the base is going to be, if you have the magnitude of this, well, that's your u vector, and so it makes sense that it's the magnitude of u. Okay, so right here, we're going to write this instead. Now the height's a little bit trickier. Since we already have this guy, which is vector v, magnitude, okay, I can always find the height by taking sine of theta equals to the height, which is my opposite, over v. Okay, so the height, which is our opposite, over the hypotenuse, which is your v vector, and then moving that around and rearranging, I actually get a formula for the height. So that's right here, and I'm going to input that right there. When you take a look at both of those together, magnitude of u times the magnitude of v times sine theta is actually the formula for the cross product, but in a magnitude form. Okay, so let's try an example. Example number 2. If you were given 2 vectors, and notice that one of them, they tried to trick us, right? They tried to put it in basis form. Like, we know what this is. We know this guy already. We can just change it. That's negative 3 for our x component, a 1j for our y, and then a negative 2 for our k. See, they try to trick us, but we're smarter than that. We also have our u vector. And what we're going to do is, if we want like a triangle, well, I mean, we know how to find the parallelogram. That was the cross product. Why don't we just split it in half to get just, like, I don't want this. I'm going to get just the triangle itself, and that's why I have 1/2 of the cross product right here. Okay? So I'm not going to go over cross product again. You're going to find the cross product, which I have in my steps, and it's going to give you a vector answer, which you'll then have to find the magnitude of using that Pythagorean theorem thing, and then make sure that you multiply it by half. So the exact answer, leave it in square root form in radicals. That's the root of 454 over 2 units squared. Remember, it's an area. But if your teacher asks you to put it in approximate, make sure that you guys put your approximation dot, okay, and round it to whatever they said to round it to. Okay, ready for more? You're like, make it stop. No, we're not going to make it stop. You're going to keep going, okay? You're going to persevere, all right? Volume of a parallelepiped. Okay, so first of all, a parallelepiped, what the heck is that? A parallelepiped is essentially a parallelogram, but a prism, like a parallelogram prism. And there's 3 coplanar vectors, A, B, and C. Let me explain what that is. Okay, just moving down. All right, so here's A, here's B, and here's C. Notice that none of them are on the same plane, like all 3 of them are not on the same plane. Okay, so that's what they mean by non-coplanar. In order to find H, I first have to look at, do you remember what B cross C gives you? Remember how the cross product, that's what I'm trying to say. The cross product is where you take both your C and your B and you create this perpendicular vector to both of those 2 vectors. That's going to give you your H, because notice that H is actually only from like here to here, right? That's your H. Your H is a projection of A onto that blue line. Whoa, mind blown, right? Okay, so here's your sun, and it's projecting your A onto that blue vector. So that is what this says over here, that H is the projection of A onto the cross product of B and C. And if I actually want to find the dot product, not the dot product, sorry, the magnitude, I'm going to have to use, and I wasn't given any thetas, what I'll do is I'll use one of the formulas. I believe this one is probably the 4th formula. Okay, this one right here. I think that's the 4th formula. Okay, in order to find out just what the height is. So I'm going to use that height to find my volume. If you want to find the volume of a parallelepiped, and by the way, this is like a pretty popular test question, what you would do is you would find the area of the base, and notice that the base, which is this guy right here, is a parallelogram with B and C on the bottom. And so if you just cross B and C, you'll get the area of that parallelogram. You're going to multiply it by the height, which we have in blue. Okay, so this guy right here. All right, and it creates this whole new formula, because these guys cancel, and you're just going to get the magnitude of A dot B cross C. Okay, and so I put that in red on the side, that if you ever wanted to find the volume of a parallelepiped, you can use this formula. And here is an example that I'm not really going to go through too much. Just be very careful when you see all of your vectors. It's probably best if you put them into vector form, like not the basis vectors. Okay, so you got to change that one up, right? And then your C was in green, so I'm just going to use this green. Okay, so I did the cross product on the right-hand side, and I put it back in. Oh, did I do the colors wrong? I did. I don't want to mess you up with the colors. I do want you to be able to follow me with the colors. There you go. Okay, so cross product on the right-hand side, and then the cross product total vector I made as orange, and I put it back into the formula. Okay. All right. Here's just another one. Take a look through it. I think you'll be able to figure it out. Again, just make sure that you put everything into like the coordinate vector form instead of the basis vectors, because it's just a little bit harder to see. But yeah, that's like a lot of application of dot and cross product. So we have one more video on that, and I would suggest that it's actually a really good idea to just organize all of this into a review sheet so that you can see it, because it is quite a bit. Okay, so again, if you have any questions, let me know.